Hi, in today's video, we're going to be talking about the concept of pipelining in computer architecture. I'm Siwa, and I'm going to be starting off the video. So the question we're asking ourselves here first is the following. What is pipelining? To make it simple, it's basically a technique that's used by our computer processor that decomposes a long complex process into subtasks or subprocesses. As you can see here on the screen, I've decomposed a long rectangle which represents the complex process into subtasks numbered from 1 to 5. The question that you may be asking yourself is, why do we realize this decomposition? We do it so that we can realize many subtasks simultaneously. That way, when the processor is trying to pass on an instruction, he can realize many subtasks simultaneously for different instructions. That way we can save time and improve throughput. So as you can see in the figure, when the processor is realizing task number 2 for the instruction number 1, the first instruction, it's realizing simultaneously at the same time the subtask number 1 for the instruction number 2 for the following instruction. So the processor is realizing at the same time, in the same time frame, subtask number 2 for a certain instruction and subtask number 1 for another instruction. That way it improves time and efficiency. So to illustrate this concept of pipelining, I'm going to be talking about a real-life example that can be an analogy to that concept, which is the laundry example. So here we're talking about the process of laundering. We're doing a load of laundry. Doing laundry can be decomposed, is a process that can be decomposed into 3 major steps, which are washing, drying, folding. Respectively, they each take 30 minutes, 40 minutes, 20 minutes, as seen in the screen here. So one load would take 90 minutes. But if now we're laundering and we want to do 4 loads of laundry, if we do that sequentially, then the whole process will take 6 hours. What does sequentially mean? Sequentially means that we wash the first load, we dry the first load, we fold the first load, and then we start with the second load. We wash it, dry, fold. We do this process 4 times, then the whole thing will take 6 hours. We're not doing any tasks simultaneously. We're just doing the whole process sequentially. We do the 3 steps for one load, then the 3 steps for the next. As you can see, that will take a lot of time. So this is where the technique of pipelining will come into action to be able to save some time. That way, we can do 4 loads of laundry, but we won't be doing them sequentially. We'll be using pipelining. We'll do several tasks at the same time for different loads to be able to save time. This will be detailed in the next slide. So if we take our 4 loads of laundry and we still want to do them, but instead we want to use pipelining, what happens to the timing? So what we do is we take our first load of laundry, we put it in the first step in the washing machine. And when it's done, when the 30 minutes are done, we move the first load into the dryer. And since the washing machine is empty, and so the resources used for task 1 are empty, we can use it for the second load simultaneously. So while the load 1 is drying and subtask 2, we can put load 2 into the washing machine, which is subtask 1. That way load 2 will be washing and at the same time load 1 will be drying. And then if we continue the process on and on, when the drying of load 1 is done, then you can move your load 1 into the folding stage, your load 2 into the drying stage, and then your washing machine will be empty, so you can insert a load 3 into the washing machine. That way you'll be folding. If you look at the third column of the drawing we put up on the screen, you can see that we'll be folding load 1. I simultaneously will be drying load 2, and at the same time will be washing load 3. That way you're saving time, and so your 4 loads, if you do this process of pipelining and you do your tasks simultaneously, the process of doing laundry for 4 loads will not take 6 hours anymore, but it will take 3.5 hours, which improved our timing, and we were capable of making better use of our time. This process will be way more efficient. But what we should note is that we're not reducing the time it takes to do 1 load of laundry, we're just reducing the time it takes to do multiple loads of laundry. This process is analogous in the processor when the processor is trying to pass on an instruction. Passing on an instruction is subdivided into many tasks. So what happens is instead of processing many instructions sequentially and taking way more time, the processor will use pipelining, meaning it will do many subtasks for different instructions at the same time to be able to reduce timing, increase efficiency, and process and pass on all of these instructions in less time.
Now that we understand the idea of pipelining a little better, thanks to the earlier example, let us see how this concept applies in a processor. We have previously learned about the architecture and use of single-cycle MIPS processor, but let us take a quick reminder on how these things work. In a traditional simplified processor that we use today to teach students, for example, we first have a program counter. We use this program counter to access the instruction memory, from which we get the instruction, obviously. Then we look at the instruction itself to decode it and figure out which type of operation it is and what registers we should read. This stage is called decoding. Once we have read our registers, we can feed them to the ALU, where we're going to do the add, the subtract, the XOR, or whatever the instruction wants us to do. It is in fact the logic decoding of the instruction that we did previously in the step just before that is going to tell the ALU exactly what to do. Once we get the result of the ALU, we could be done and just write the result to a register, or we could have a load or a store instruction, in which case what the ALU computed is really the address that we use to access the data memory and not just the result, the answer itself. And what comes out of the data memory is what we end up writing to the registers. Now, of course, there are a lot of things to do with branches and jumps and so on, but basically we can do one instruction per cycle, as it essentially goes through these 5 stages. First, starting at the PC, fetching the instruction, then accessing the registers, after that doing the operation in the ALU, accessing the data memory, if needed of course, and finally writing the result back to the registers. Now in this case, for example, the time to do the whole thing might be something like 20 nanoseconds. So if we had this kind of single cycle processor, we could have one instruction being completed every 20 nanoseconds. But the processor does not actually use most of the hardware if we handle instruction one by one, using the single cycle way that we just said. Very similarly to the concrete example of the laundry, we are not actually using the full capabilities of the hardware available. So to compensate this large inefficiency, the concept of pipelining can be introduced to processors. And so the idea of pipelining can be explained through this table. The rows are the different stages of the processor. We have our fetch, decode, execute, memory, and write. And the columns are the increasing clock cycles. For example, here we show what happens in cycle 1, C2, C3, C4, etc. Now, usually, without pipelining, we will first fetch some instruction A during cycle 1. In cycle 2, instruction A moves to decode. Then in cycle 3, instruction A will be doing the ALU. In C4, A will move to do memory. And finally, in C5, A will write the result in the register. And in the next cycle, we can begin fetching the instruction B. If we do that, then we really will finish one instruction every 20 nanoseconds. However, if we apply the idea of pipelining, in cycle 1, we're still only fetching instruction A. But in cycle 2, we will be decoding instruction A, and we can begin fetching instruction B as the first part of the processor will be unused and available. And this holds for all stages of the processor. When instruction A moves to the execute stage, B will move to be decoded, and we can start fetching C. In the cycle C4, A is in the memory stage, B will be doing the ALU operation, C will start being decoded, and D will be fetched. And finally, when A is in the last part of the pipeline, B will be right after it, or actually before it, in the memory stage. C will be doing the operation, D will be decoded, and we will be fetching instruction E. So now, the idea is that we don't have to wait a full 20 nanoseconds between each instruction to be completed anymore. Once the instruction A leaves the pipeline, very soon after it, B will leave the pipeline, then C, then G, etc. If we divide this previous 20 nanoseconds into 5 equal pieces for each stage will take approximately 4 nanoseconds. And so, even though the latency to do A is still 20 nanoseconds, which is, by the way, also the time needed to fill the pipeline, the throughput will be one instruction done every 4 nanoseconds, the time for each stage. Once A leaves the pipeline, 4 nanoseconds is how long it takes for B to leave, and then we just keep pulling instructions out. So, similarly to the previous example, it takes a while to fill the pipeline, but when it is full, instructions are getting done very quickly. Let us take one last concrete MIPS example, just to reinforce our understanding. If we want to load 3 words from the data memory to our registers using the MIPS instruction load word or LW, it usually takes the processor approximately 800 picoseconds to complete each instruction. So, using the single cycle method, loading 3 words should take us more or less 2400 picoseconds. But if we use the pipelining method, by superposing each stage like we did before, the throughput of the whole operation should not exceed 1200 picoseconds. That is more than half our previous result. So with this example, I hope you get the idea how much pipelining can improve performance, although it is not perfect, of course, and that is what we'll see next.
So if we use pipelining in our processor when we are passing on instruction, ideally our CPI is supposed to be 1, but in practice we realize that it's not actually 1. If we come to look at why that is, what we can talk about is pipeline stalls. So what are pipeline stalls and how do they affect the fact that the CPI will not be 1? So take this image shown on the screen. We have the 3 subtasks of the complex task that we want to realize. 1, 2, numbered 1, 2, 3. So if the processor starts by trying to pass on the first instruction, it goes through task 1, and then it goes to task 2. If we're using pipelining, that means that a second instruction should go to task 1 simultaneously. We'll be doing task 1 of instruction 2 and task 2 of instruction 1. As explained before, if we keep on doing the process and then we introduce a third instruction, for example, then as you can see, each ball represents a certain instruction and what task we are performing of the said instruction. So imagine there's a certain hazard that will be detailed by another colleague, how hazards happen and why they happen. Like a mistake, for example, in task 2 for the blue ball here, which represents the second instruction. So imagine there's a hazard, that means that we stall a bit in that task. It takes a bit more time. So what happens is simultaneously task 3 of instruction 1 will be done. But task 2 will still be in progress. That means that instruction 3, which is the white ball that is at subtask 1, cannot move on to the second task because task 2 is still in progress. That means that we'll have 2 idle blocks, which are the task 1 and the task 3. They'll both be idle and they won't be working. This whole process will cause a delay in the pipelining technique. And it is because of those stalls that the CPI cannot be 1. It will be necessarily more than 1. Because it's only if the pipelining goes smoothly with no pipeline stalls that the CPI will be exactly 1. But since we have those stalls that happen actually with the processor, it cannot practically be 1.
So, to conclude, pipelining is a great way to reduce the overall time needed to complete a process. By superposing substages in unused hardware elements, like we saw, the throughput of a code can be extremely reduced. We are using every aspect of the processor, hence making it as fast as practically possible. But the process can seem a little bit too good to be true. Indeed, although the method gets us very close to a perfect performance. This means that we have a CPI equal to 1. In reality, the technique remains kind of flawed because of various hazards and dependencies that can happen, which will be discussed in another video. Anyhow, I hope the idea of pipelining is now clearer for you guys. That was Frederic Zein and Siwa Dakroub in Shab Academy.